Computers eating the grid. You need 1 year to build a data center. You need 7 years to connect it to the grid. Today, we're going to talk about what is powering AI. You've probably seen stuff like this. AI energy wars will get worse before they get better. The AI energy crisis. Sam Altman defending AI's energy toll. The AI energy bill problem. Today, we're going to talk about this. We're going to talk about electricity. We're going to talk about data centers. We're going to talk about how data centers are being powered, how they will be powered. We're going to talk about moonshots, and we're going to talk about open questions. We will try not to talk about AI. We will try not to talk about bubbles. I'm Skander. I'm a 3-time founder in the US and Europe. I actually had a data company working in AI before, and now I run Climate Drift, where we help build climate solutions and deploy leadership into climate. So first, what happened so far? What is a data center even? Like a data center is a row of computers. Everybody knows that. In principle, it's a giant room full of computers whose only job is to remember things and answer questions really fast. That's kind of like the baseline. Thanks to the data centers, we have the internet and we have AI. If AI gets unlimited energy, this is how the world will look like. We use data centers not only for AI, like this video that you're seeing on some feed somewhere is also hosted in a data center. But if you want to learn more about data centers, 15 minutes, I'm not going to cut it. Ben and my friends at Step Change made this very nice 4-hour-long video on data centers. Data centers right now is a hype like no other, right? Like as a capex share of US GDP, it is bigger than the Manhattan Project, the Apollo Project, and the broadband build-out combined. We are building a lot of them right now, right? So US data construction is now overtaking offices. And this is just the beginning of a wave, right? Ned Bullard forecasted that like we're just beginning to see the wave of data center build-out. The whole like forecasting question is actually quite interesting, right? My favorite quote comes from a Virginia-focused energy economist that says our forecasts for 32 are probably off by a factor of 2, but nobody knows if it's 2 times too high or 2 times too low. That's because of this one. It's a core question of like, are we spending too much or just enough on data centers? Sundar and Mark put it quite well. The risk of underinvesting is significantly greater than the risk of overinvesting. And in the very worst case, we have just pre-built for a couple of years. So in the end, who the fuck knows, right? But if you followed the markets in any way, nobody is sure if the capex spend currently makes sense or it doesn't. What makes true for sure is that data centers consume 1% of global electricity right now. And just to put it into context, that's like household devices, TV, phones, everything that you have running right now uses 2% globally. To put it in like even larger numbers, a large data centers, which we measure in electricity, so a 100 megawatt data center currently uses the electricity equivalent to 350,000 car EVs annually. And now we have 12 gigawatts of new data centers capacity under construction and like an extra 60 plus gigawatts planned. What does that even mean? So a city of 1 million people in the US, that would be Denver, for example, uses 1 gigawatt. So just to you have a comparison. Where are we building data centers? Essentially everywhere. Everywhere we use the internet right now, we're building data centers. By 2030, if the build out continues, they could use around 10% of the electricity of the United States. Although it might be more or less again, because all these forecasts are either higher or lower dependent on, well, we don't know. Well, like Andy Luberstein from EIP has this very nice framework. It's due to AI demand and profitability. Nobody knows how much AI we actually need. If there's potentially unlimited demand, and with the return on investment for it, it just makes sense to build data centers. There's also the question of like algorithmic evolutions, because AI is an AI, and our software is getting better, and the question is like, will efficiency go up? That is also true for the computing hardware efficiency. Every year at the NVIDIA conference, we see cool new chips that are X times better than the last. But like, what is for sure a constraint is the whole power supply, because yes, you can develop software really quickly. Yes, you can develop chips fairly quickly, but putting steel in the ground and creating power plants just takes time. To all efficiency questions, we should probably talk about Jevons Paradox, right? The Jevons Paradox is actually coming from the coal age. It means that if a data center becomes more energy efficient per computation, the cost of computation drops, which makes it cheaper, which drives much more demand, which means that more compute is being used, which means the total energy consumption actually increases. And we're currently seeing that. Those are the latest numbers for token price costs and token price consumption, right? It goes down, it goes up. So Jevons Paradox proves efficiency will not get us there. And then there's a whole question of like announce and build. You've seen the large wave coming. It is a wave. Like a wave also crashes at one point. And not everything, like again, it's a forecast, so nobody knows if the wave is going to actually happen as it is. There's currently estimations that like 40% of the announced data centers will probably never get built. But back to the topic, what is the electricity actually used for? it's used for computers and cooling mostly. So around 40% of the electricity goes into servers and 40% goes into cooling and power provisioning. So where's the electricity coming from? The grid, you would say, right? Where everybody gets their electricity from. And we're going to look at this. In the grid case, it would be the following. You have generation, power plants that are utility owned, going to over transmission lines, going to the data centers. So, how our data centers powered? Well, fairly straightforward. We just need to check today's global electricity mix, and you see it's mostly coal, gas, and then renewables. But if you look at the numbers, actually, you see that only 45% of currently planned data centers will be grid connected, and 43% will be TBD. What does TBD mean? So what you need to understand is that for data center developers, speed is the mode, right? We need to get faster at building these data centers. We need to connect these data centers right now because the AI hype is right now. And the quicker you have a data center online, the quicker you can build AI use cases. Today's reality thus means essentially shut up and take my money. So the more money we can throw at the problem, the quicker it gets solved, the better it is for everyone. And I will kind of start with him. The problem is that in principle, nobody likes waiting in line. And, Texas is a very good example. Texas currently has more data centers coming online than all other states. And by states, I mean not only US states, but globally, right? Than any other country in the world. The problem is, again, nobody likes waiting in line. And ERCOT, which is the US, the electricity market for Texas, large load queue, so the amounts of large projects that want to connect to the grid, has nearly quadrupled in a single year. 77% of their load comes from data centers. Why is that? We need a year-ish to build a data center. So this is the Stargate data center by OpenAI and SoftBank. On left side, you see 24, essentially nothing was there. In 25, we already have 2 of the data centers there up and running. If it takes a year for a data center, but the waiting is so long that it takes 7 years to connect it to the grid, something else must have happened. The electricity is not coming from the grid. Don't forget it's a race. The electricity is coming from bring your own grid. So you bring generation right next to the data centers, and then you're not dependent on the pesky grid, and you don't need to wait in line. Anyway, it goes back to this guy. So Elon's data center, Macro Heart, actually started with the whole bringing in gas turbines that were originally scheduled for emergency use, and you can see you can put them on trucks and you can literally just ship them in. Everybody thought, wow, what a great idea, right? So of all the data centers that are right now planned, a lot of them are planned as behind the meter data centers, and behind the meter means behind the grid, right? Independently having generation. And if you look at what tools and what equipment they actually ordered, it's mostly gas turbines and engines. So it's all gas. You say, okay, perfect. The answer is all gas. Well, spoiler, it has always been gas along because of this. The US is a petrostate, right? If you look at the current US and future US grid, the natural gas, which is the violet thing on the side, is continuously growing. And it's also true for exportation, right? US has become one of the main producers and exporters and users of liquefied natural gas. If you want to learn more about the whole gas country USA story, there's a very good Climate Town episode on it, Secret Life of Natural Gas. Highly recommend you to check it out. The bottleneck now becomes, how do you actually make that gas into electricity, right? And for that, you need gas turbines. If you check gas turbines, you would expect these gas turbines manufacturing to also explode like we see in data center world. But history rhymes, right? So we already had this. They have already seen this in 2000 around the dot-com bubble. And there was a huge build out of also data centers. And the expectation is that a lot of natural gas turbines would be needed. Production exploded, but then demand cratered, right? Dot-com bubble burst. The gas turbines manufacturers actually remembered this, and they went into it and said, okay, it's better to be profitable and undersupply the market than go bankrupt and oversupply the market. Right? So this is why gas turbines from normal manufacturers are probably not going to cut it, because they're not ramping up productions super strongly. So what's happening now is that every turbine is coming to the rescue, right? So this is Boom Supersonic. They're building a supersonic plane, think Concorde, but modern. And they just announced that they raised $300 million in new funding and are selling their turbines to power AI data centers. This is a ship turbine. This is also now being retrofitted to actually run data centers. And it wasn't only gas, to be fair, right? Nuclear was also on the graph, because the future of nuclear is probably just 10 years away, right? Google and Amazon are strongly investing and already buying offtake from a small modular reactors. So they're buying electricity from reactors that don't exist yet, that are currently in development. And Microsoft is even going back and helping to restart 3 Mile Island. So how are data centers powered? We understand that now they're powered by gas. We understand in 10 years they will be powered by nuclear. But like, what happens in the next 5 years? What happens in between? So what else is there? We could put our data centers into space. People are obviously working on that. That's literally from this week NVIDIA presentation. And like, some people find that pretty crazy. Sam Altman already like ridiculed the idea. Elon Musk said it is 100% feasible, and they're building it. So, we're going to find out. What else is there? We already saw fusion. That's kind of like the good news. And by fusion, I mean solar. So this is the global electricity mix. And, you see coming up to the side is wind and solar is exploding. Let's zoom in. So solar is really taking off, right? Like, so the actual installations of solar have been 3 times higher than all the 5-year forecasts. We're just so good at building solar and deploying it at this point. Well, we mostly means China. So China installed more than twice as much solar than the rest of the world combined. But this kind of like brings me to like the side point that, like, if AI is a race for electricity, it kind of already has been decided, because China has been growing their electricity generation tremendously, while the US has fairly stagnated in their electricity usage production. But like, to be very fair, there's companies in the US that are doing like God's work there, right? So Intersect is a company that for years has built out large scale renewable sites with large scale load sites. In this case, data centers, and it was just bought by a sweet $4.7 billion in cash by Google, because Google understands if you want to have power, you need to own power, you need to construct power, right? So this is Carolyn Golan, Google's former global head of energy. And 5 years ago, vertical integration didn't make any sense. Now it does, because there's no way to procure the option on power in this country unless you own it. Let's quickly talk moonshots. So geothermal is kind of like the poster child of moonshot electricity generation this year, because we have the poster child of geothermal, Fervo, IPOing, and they already signed offtake with data centers. The fusion race is also on, right? So private fusion investment is approaching $10 billion now, of most of that in US and China. And then there's a whole like overarching question of like, are there more moonshots like this? Andy Lubershane made a very nice series. In case you want to listen and watch it, my friend Hugo from New Wave is publishing a series on this. For me, the question with like moonshots is always like, history has shown us that it takes a long time from invention of something, first, lab scale product, to actually bringing it to market, to commercialization. And then it takes a very long time from commercialization to actually mass market uptake, right? Obviously, that can strongly change for specific technologies, but we see that it takes time to invent something and then bring it to market. And this will be true for all the technologies out there, because it's one thing to invent it and it's another thing to actually keep it running. For another time, we should talk about impact. I want to shout out to Tracy from Waymo, who built a very nice presentation on climate drift for energy use, environmental impact, and workforce impact. For another time, we also need to talk about water. Asinometry has a very nice video on the data center water problem. We also need to talk about emissions, because thanks to the data center build out in AI, every big tech company is currently missing their emission targets. For another time, we also need to talk about solutions, because there's a lot of ways to decarbonize data centers. And we also need to talk about, can we take AI and actually make the world a better place? There's a lot of applications around AI and climate. Is at the end? Well, I don't know. I had 15 minutes. Like, subscribe, give me a comment. Let me know if I should make more videos like this.